What if I told you there's a whole hidden dimension to numbers? One that takes problems that seem impossible and turns them into these beautiful, elegant solutions. Well, today we're diving headfirst into that world, the world of complex analysis.
Our whole journey kicks off with this one question, a question that for centuries felt kind of like a mathematical joke. What number, when you multiply it by itself, gives you -1? I mean, in the world of real numbers we all live in, there's just no answer. And listen, this wasn't just some brain teaser for fun. Mathematicians were literally hitting a brick wall with this thing when they were trying to solve very real problems, like figuring out the roots of polynomial equations. It was this frustrating roadblock that just stopped progress cold. So the big breakthrough, it wasn't some new formula or a clever bit of algebra. Nope, it was a total leap of imagination. Mathematicians basically said, okay, if a solution doesn't exist in our world, we'll just have to invent one. And just like that, I was born, the imaginary unit. And please, don't let the name fool you. It's not a trick. It's a brand new, fundamental piece of the puzzle defined by one simple, elegant rule. I² equals -1. This one little idea is the key that unlocks everything else we're about to see. Okay, so we've got this new number, I. Fantastic. But where does it live? I mean, where do you put it? To figure that out, we have to map out a whole new world, the complex plane.
You remember the number line from school, right? Just a single straight line holding all the numbers we're used to, positives, negatives, all of it. But it's a crowded, one-dimensional street, and there is absolutely no room for our new friend I.
All right, this is where it gets really cool. Imagine taking that number line we all know and laying it flat. That's our real axis. Now, add another line, a vertical one, crossing right at 0. That's our imaginary axis. And bam! Suddenly numbers aren't just points on a line anymore. They're locations, coordinates on a two-dimensional plane. Any number z equals x plus iy is now a specific spot on the map. So take a number like, say, 3 plus 4i. What does that even mean? Well, it just means you go 3 steps along the real axis and 4 steps up the imaginary axis. Boom, you've learned it on a specific point. And now that it's a point in space, we can do cool things like measure its distance from the center, its modulus. A number now has geometry. How cool is that? Okay, so we've got our map, we know the layout of this new world. Now let's talk about the rules, the physics of this place. And the biggest rule is this. Functions here aren't just for crunching numbers. They're like reality warping machines. And I'm not just being dramatic here. As the textbook for this stuff, Brown and Churchill, puts it, this whole geometric view is the central idea. A function of a complex variable is really a mapping or a transformation. Now check this out. This table is wild. It shows what a super simple function, w equals z², does to the plane. You take a perfectly straight vertical line, and this function bends it into a parabola. A horizontal line becomes a different parabola. And this is the craziest part. You see that first quadrant, that simple corner? The function grabs it and unfolds it to cover the entire top half of the new plane. It's incredible. So, the takeaway here is huge. In this world, functions don't just calculate. They physically stretch, rotate, and warp space itself. All right, so this idea of functions warping space, it has some massive consequences, especially when you bring calculus into the mix. This is where we meet the superheroes of this world, analytic functions. And this chart just lays it all out perfectly. Think about regular calculus. Functions can be, well, a mess, right? They can have sharp corners, breaks, they're unpredictable. But in the complex world, these analytic functions are the total opposite. They are unbelievably smooth. And get this is their superpower. If you can find the derivative of an analytic function just once, you automatically know it has infinitely many derivatives. It's a level of elegance and predictability that real numbers just can't touch. So, what does analytic even mean? Well, a function is analytic if it's differentiable, or smooth, not just at one single point, but in a whole little area around that point. It's like a perfectly polished surface with absolutely no bumps or scratches anywhere in a given patch. And that strict rule is what gives them all their amazing powers. And this smoothness thing, it's not just some neat mathematical trick. It leads to results that honestly feel like magic. It lets us do things that should be impossible. Okay, so let's see how all this beautiful theory actually gives us some incredible power in the real world, giving us these surprising shortcuts for problems that are usually a nightmare.
If you're an engineer or a physicist, you see integrals like these all the time. They pop up everywhere, from signal processing to analyzing waves. And trying to solve them with regular calculus, oh man, it can be an absolute grind. But complex analysis comes to the rescue with this amazing toolkit called residue theory. It basically lets you solve a lot of these tough integrals by taking a little detour through the complex plane. It turns a massive headache into something you can often solve with astonishing ease. It's like finding a secret tunnel that bypasses all the traffic. And believe me, this isn't just about making life easier for math students. The ideas from complex analysis literally shape the physical world around us in ways you probably never even thought about. I mean, just look at this list. The exact same math we've been talking about, z equals x plus iy, is used to model the electric fields in your electronics, to figure out how heat flows through an engine block, and to analyze how air flows around a plane's wing. It's the hidden mathematical language behind huge fields of physics and engineering. And that right there is the magic of it all. These abstract rules we invented for an imaginary number plane turn out to be the perfect description for how a real airplane wing flies or how an engine heats up. So we've taken this quick tour through a hidden dimension of math. What's the big takeaway here? What should you remember? It really all boils down to the power of imagination. Think about it. We started with a question that had no answer. And just by daring to imagine a solution, we didn't just solve a little puzzle. We unlocked an entire new way of thinking, a whole geometric world that gave us these unbelievable tools to describe our own reality. So it really makes you wonder, right? If one impossible number could do all of that, what else are we missing?